For this learning result, it kind of says if you kind of hope or believe or know that almost all of the Fourier coefficients are on small degree, like all the large Fourier coefficients are on small degree sets, then you can learn it in time n to the k, where k is your bound on the number of the size of the coefficients, which is also the number of sets of size at most k. There's a variant of this result that's also very important in learning. If you just know or believe that there's some collection of, let's say, about n to the k sets, not necessarily all the small cardinality ones, but some collection out there of n to the k sets that has almost all the Fourier mass, in the sense that the sum of the squares of the Fourier coefficients not in this collection is at most epsilon, then you can have the same learning result, but it only works in a different model of learning, the model of learning where you have membership queries. That means not only can you just get random examples from the function x f of x, but also you have the power to say, just tell me f's value on x's of your choice. So somehow if you have that membership query power, there's another algorithm due to kind of Goldreich and Levin, or Kushlevitz and Mansour, which sort of lets you find the location of all the large Fourier coefficients and thereby learn the function. In the low degree algorithm, like, you just hope that it's the low cardinality sets that have most of the Fourier coefficients squared.
Membership squares are necessary here?
Well, we don't know how to do it without them. I don't know if it's somehow provably necessary, but seemingly. Okay, so well, there's other reasons to study Fourier coefficients, but in particular, these two theorems actually motivate you to try to understand how can we prove that, given kinds of functions that are represented in different ways, maybe by decision trees, or maybe they're small DNFs, or maybe they're monotone, how can we prove that they have kind of simple Fourier spectra, that like almost all of the Fourier mass, or almost all the probability mass of the spectral sample is concentrated on a small collection of sets, especially on the small cardinality sets. Okay, so this property here, let me just call it Fourier concentration. Okay, this is sort of Fourier concentration. You can say that the Fourier spectrum of f is concentrated on sets of cardinality at most k. How can we show that various functions have small Fourier or a good Fourier concentration? So I'll have time here to tell you about one method of showing this, and it's by studying something called average sensitivity of Boolean functions. So let me erase this one now. And before I can tell you about average sensitivity, which is sort of a quantitative property of Boolean functions, I need to tell you about a similar property called influences. So I'll start with this definition of something called influences. Okay, so this is the definition. Okay, so for a Boolean function, which again we write with plus or minus 1 notation, and also for a coordinate I between 1 and n, I want to look at something called the influence of coordinate I on the function f. Okay, this is the influence of coordinate I on f. It's a number between 0 and 1, how much sort of I influences the function. And this is the definition. It's just probability over a random x, uniformly random x, that f of x differs from, I'll invent some funny notation here, f of x. This means with the ith coordinate negated. Okay, where I just invented this notation, x plus I just means x1 up to xi minus 1, negative xi, and then the rest. Okay, so the experiment is you pick a random input string, you look at f's value, then you flip the ith coordinate, looks at f's value, and you ask, did that change the value of f? Okay, did flipping the ith coordinate change the value of f? And the probability with which that happens is the influence of I on f. Okay, Now, you might have actually remembered one of the first examples I did was concerned with this thing, f hat I. This is like the coefficient on just the singleton xi in the Fourier expansion, the polynomial representation of f. And we saw that this equals the expectation of a random x of f of x times xi. And I kind of said that that also measured, well, this sort of measures the correlation of f with the ith coordinate. So let me compare them, because these turn out not to be the same thing, but they're somehow related. So how are they related? Let's actually do some examples. Well, this is, let me just also write it. It's the probability of a random x that f of x equals xi minus the probability that they differ. So let's do some examples, and then we'll see some things about the relationship between them. Okay, so let's see. Let's say if f of x is x1. It's an extremely simple Boolean function where you ignore all the bits except the first. You just output the first bit. Well, then what is the influence of coordinate 1 on this function? 1, because if you flip the first bit, that indeed always flips the value of the function. And what is f hat 1 here? It's also 1, because this is like visibly the Fourier expansion of the function, and the coefficient here is 1. Okay, so there they were the same. But they're not always the same. Let's see if f of x is negative x1. Okay, you just negate the first bit. And the influence is equal to? It's still 1, because it's still the case that flipping the first bit flips the value of the function. The Fourier coefficient is minus 1. It's sitting right there. Let me do one more example. F of x is the parity of all the bits, or the XOR of all the bits. So what is the influence of the first coordinate here?
1.
It's 1. No matter what x is, when you pick it at random, when you flip the first bit, that flips the XOR of all the bits. But the Fourier coefficient is 0. Because, well, the Fourier expansion of this is just this. There's nothing on x1. Okay, so they're not always the same. For example, the Fourier coefficient, this is always between minus 1 and 1. But this one is always between 0 and 1. They have some relationships, though. But really, okay, this influence is somehow the influence. This is more like the correlation of the first coordinate with the function, which, well, it's this. It can sometimes be negative, for example. But what is the relationship here? Let's try to understand it a little bit more carefully. So these two quantities are looking at sort of the same object or same situation, but kind of counting it in different ways. So let's say we're interested in the influence of the ith coordinate versus f hat on the singleton set I. We can imagine drawing the Boolean hypercube, sort of splitting it into two parts according to like the ith direction. So the Boolean hypercube has like all these edges in it, where these edges are strings that differ only in the ith coordinate. So maybe up here is where xi is plus 1, and here down here is where xi is minus 1. So there's 2 to the n minus 1 points down here, and 2 to the n minus 1 points over here, and they're like matched up according to the same except in the ith coordinate. And in both these expressions, you kind of look at all of these. It makes sense to look at all these edges together and understand f's value here versus f's value here. So if you have some function f, and we look at an edge, well, these 2 points actually sort of show up. They show up sort of twice here and twice here, according to whether x is this one or this one. In any case, sometimes f's value is plus on this point, and it's also plus on this point. And in that case, it kind of contributes, the contribution to the influence is 0, because these have the same values. And also the contribution to f hat on the singleton set I is also 0, because if you look at this edge, like one time you're getting that f of x equals xi on the top, and one time you're getting that it's not equal, and then you're subtracting them, so they kind of cancel out. Like I'm imagining computing these two things, influence and this thing, like sort of edge by edge. Similarly, maybe for another edge, it could be that f is minus here and minus here, in which case the contribution to the influence is again 0, and the contribution to f hat I is 0. But sometimes f gives different values to these two functions. So sometimes f is plus on the point on top and minus down here. So that's the case where they differ. So it sort of contributes 1 or 2, depending on how you look at it, to the influence. And it contributes the same amount to the correlation. This is a case where like f is positively correlated with xi. The last possibility is that f's value is minus here and it's plus here. And sort of here we count 1 also for the influence because they differ. But in the contribution for f hat I, we count -1 because here's a case where like f is like negatively correlated with xi. So maybe you didn't like catch all the numbers exactly, but I don't want to write a formal proof because it'll take a little time. But let me just say that this implies the following facts. So the consequences of this is, first of all, f hat I, the singleton set, is always at most the influence. And let me just add that they're equal if, let me not say, well, I could say if and only if, but let me just say if this case never happens, then they're equal. And one case where that doesn't happen is if f is monotone. F is monotone in the ith direction means like this never happens. So I can say if f is monotone. I guess I can say, if I'm not making a mistake, it's actually if and only if f is sort of monotone in the ith direction. But I don't know if I'll use that. Let me just say that. OK, so that's the relationship between these two quantities. Actually, I'm mostly going to be concerned about the influence from now on. Is there any more chalk? Anybody know? No? OK. Oh, goodbye. OK, let me just do another example, too, so that we're understanding each other. One Boolean function that I care about a lot, it's like one of my favorite functions, is the majority function, but on all n coordinates. Okay, so you take all n inputs and you output the majority of the truth values. Assume n is odd, so there's no ties. So let's compute the influence of, let's say, the first coordinate on the majority function. Okay, this is like you pick a random string, see what the majority is, then you flip the first coordinate. I could have chosen any coordinate, it's symmetric. You flip the first coordinate and see if that changes the outcome of the majority. Well, how could it happen that like that first person could change the outcome of the majority? It's only going to happen if the rest of the bits between x2 and xn are exactly split 50-50. That's exactly the cases in which flipping the first bit makes a difference. Again, assume that n is odd. So it's really the probability over x that x2 through xn are exactly split. Okay, so it's like you flip n minus 1 coins, and what's the chance you get exactly half heads? Yeah, it's proportional to 1 over root n. You can write down a more exact expression, but it's something like that. Okay. And actually, this is nice because majority is an example of a monotone function. Monotone means that if you change some of the input bits from false to true, it can only change the outcome from false to true. So majority has that property. And that means actually this influence is equal to the degree 1 Fourier coefficient. So there we equally well computed this quantity for majority. Good. So, right. So influences are a natural quantity, measuring the importance of a of a coordinate to a function. And now I'll show you that there's a very simple formula for the influence of a coordinate in terms of the Fourier coefficients. So this is another example of this kind of point of Fourier analysis, this philosophy that if you know the Fourier coefficients of a function, it tells you some interesting, nice, simple properties about the function. So here's what I want to prove to you. Proposition. The influence of coordinate I on a function f is equal to, you look at the sum of f hat s squared. Remember, if I summed up this over all s, I always get 1. That's a basic fact. But I don't sum it over all s. I just sum it over the sets s that contain I. That's very elegant, I think. I mean, you just look at the sets that contain the coordinate I that you care about, and you just add this up. And it gives you the influence. Okay? Or if I want to write this, sort of testing your understanding in terms of this spectral sample, what would the event be? Pardon me?
Probability of SF is equal to S overall.
Probability contains I.
Yeah, it's a probability that SF contains I. Right? Because you just these are all the probabilities for being various sets capital S, and you only want the ones that contain I. Great. So let's prove this. Okay, so let me define another function. I have f, but let me define another function f. I'll call it minus I, which on input x1 through xn, it's just basically the same as f, except I'm going to negate the ith coordinate, the ith coordinate. Okay, that's another Boolean function. And now let me look at the expectation of a random x, of f of x times this f minus I of x. And for a second, just think of f minus I as just some other function, g. Okay, so we're looking at expected value of f of x times g of x. Again, these are both taking values plus or minus 1. So this whole product is 1 when they're the same, and it's minus 1 when they're different. So therefore, this expectation is probability over x that f of x equals f minus I of x minus the probability that they're different. And we also just use that the probability that they're equal is 1 minus the probability that they're different. So this is 1 minus 2 times probability over x that f of x differs from f minus I of x. Okay, and what is this probability equal to? The influence of I on x. That's on f. That's exactly the definition. Okay. But now we'll also compute it in a different way. Compute it here. So I'm going to use this Parseval formula that tells us that whenever you have the correlation between two functions, it's also the correlation between the Fourier coefficients. So if I'll call this star equals the sum over all sets S, f hat S, f minus I hat S. Okay. So now if we could only understand the Fourier coefficients of f minus I, we'd be in good shape. But that's very easy, right? I mean, how do we understand f minus i's representation as a polynomial? Well, we just take f's representation as a polynomial and replace xi by minus xi. And what effect does that have? It gives you a negative on all the coefficients of monomials that include I. So I guess I could say it like this. F minus I hat S is f hat S if S does not contain I, and it's minus f hat S if S contains I. I hope you can see that just by imagining the polynomial representation of f and imagine plugging in minus xi for xi. Okay, so putting these two things together, this is going to be the sum over all s that contain I of f hat s squared minus the sum over all s that don't contain I of f hat s squared. And remember, if you add up all the squared Fourier coefficients, you get 1. So this part is 1 minus this part. So then it's just 1 minus 2 times this part. Wait. What happened here? This was like this, right? Thank you. Okay. And that completes the proof by comparing it with that. Okay. Any questions about that?
So for monotone function, most of the terms are just 0 in the summation.
For a monotone function, both of the terms are 0.
Like in the summation of the definition of influence.
This is squared and that's limit.
Oh, okay.
In this thing?
Yeah.
Yeah, this is, I guess, a formula. Yeah, no, it's not the case. So for monotone functions, you have this funny fact that if you add up the squares of all Fourier coefficients of sets that contain I, you happen to get the non-squared f hat of the singleton set I. It's sort of a crazy fact that is nevertheless true. Okay. All right. Okay. All right, so that's a nice concept. Now let's move on to the next one. And this next concept, which is called average sensitivity, is going to be one way that one technique you can use to show that certain simple classes of functions also have simple Fourier spectra, that almost all their Fourier coefficients are on small degree sets. And for example, they're therefore efficiently learnable, among other things. Okay. So average sensitivity is a very nice, also simple concept. So the average sensitivity of f, I'll write it as of f, it's just the sum of all the influences. Okay, actually so far that doesn't look too natural, but I'll show you by continuing the inequality. It's actually quite natural. So I'm continuing. That's the definition, but now here are some calculations. Let me first write the definition of influence. That's the sum, I goes from 1 to n, probability over a random x that f of x differs from f of x with the ith coordinate flipped. And let me just write the probability as the expectation of an indicator. The indicator, random variable that f of x differs from f of x with the ith coordinate flipped. Okay, well, I do that so that I can interchange the sum and the expectation. And now what's going on in here? I pick a random x, and then I go through all the coordinates between 1 and n, and I look, hey, is f of x different from what I would get if I flip the ith coordinates? And whenever that happens, I count 1, otherwise I count 0. So effectively this sum, if you think about it, it's counting the number of coordinates I for this given x, such that flipping that coordinate would make a difference to f's value. That's hence the name. So this is the, well, it's the average over x of the sensitivity of f at x, which means the number of coordinates I such that f is sensitive on this coordinate at x. So f of x differs from f of x plus I. Really getting sort of desperate on chalk here. Let's try this one, I guess. Maybe end early. So let's do some examples. Yeah, we don't need this proof anymore. Oh, thank you. Yeah, that's pretty good. Let's do some examples. Okay, so what's the average sensitivity? Here's a good example of the parity function, the XOR function on all coordinates. Someone could say? It's n, yeah, because if you pick a random string x, it doesn't matter what it is. All of the coordinates have the property that flipping them changes the parity. Maybe we'll do the average sensitivity of the function x1, just output the first bit. This is 1 because, again, it doesn't matter what x is. If you flip the first coordinate, it changes this function. Otherwise, it doesn't. Or the average sensitivity of the constant function, thank you, is 0, because you never change the value of the function if you flip any coordinates. Maybe we'll do one more here. Well, the average sensitivity of the majority function on n coordinates. Well, one way you can do it, I mean, we could have done it these ones too, is well, you could just add up all the influences. We computed for majority that an influence of each coordinate is like 1 over root n. So this should be proportional to n times that, so theta of root n. Another way to see that is, if you pick a random string and compute the majority, and then you imagine flipping coordinates to see if that changes the value of majority, most of the time it doesn't change anything, right? As long as the majority is like a slight supermajority, then it doesn't matter. The only chance you have of changing the value of the majority is in the case where like exactly ceiling or floor of n over 2 of the bits are +1, okay? And in that case, the sensitivity is very large, like about half of the bits you can change in order to flip the majority's value. So this is like n over 2 or so times the probability that a random string will be right on the boundary, which again we know is proportional to theta 1 over root n. So I guess I sort of said the same heuristic calculation a couple of different ways, but that's the answer. Okay, so the average sensitivity of a Boolean function is somewhere between 0 and, well, the most this could ever be is n, right? And it's actually thus achieved for parity. So it's a number between 0 and n. Okay? So, under this interpretation, average sensitivity is like, again, it's like a nice kind of interesting combinatorial probabilistic property of a function. But we can also give it a nice Fourier formula. And that's kind of straightforward because we had a nice formula for the influences, so we just have to add it up and we'll get a nice formula for the average sensitivity. So let's do that. So on the other hand, well, the average sensitivity of f, it's the sum, I goes from 1 to n, of, now we'll plug in the formula for the influences, of the sum over all s that contain I, of f hat s squared. Okay, now we'd like to reverse this sum. I always have to take like a couple of seconds to remember how to do that. So I want to sum over all subsets of n. And now how many times do I count f hat s squared in this double sum? I count it once for each of its elements. So I actually count the cardinality of s times. Okay, so this is the nice formula for the average sensitivity. In fact, now again, test your understanding of this weird definition. How would I write this in terms of the spectral sample? Exactly, yeah. So this is also the expectation. This is over the spectral sample of the cardinality of the spectral sample. Again, this is kind of like, when you draw a set from the spectral sample, it kind of tells you a subset of coordinates that are somehow important for the function. And the average cardinality of that set is actually equal to the average sensitivity of the function. So for example, you can maybe now see that this can help us show something about, well, the typical size of this set. The learning algorithm works well when there's very small, where there's only small Fourier coefficients above a certain degree. That's like kind of saying it works well when this set is typically small. So that's kind of like saying it should work well when this average sensitivity is small. And that's like the connection between, I don't know, simple properties of a function and like learning via this Fourier method. Yeah.
So is the spectral sample the same as sampling of uniform random x and then taking a set of sensitive coordinates to that x?
No, although it's a very good question. I was discussing this with Clément over here. You can do that same thing. Here's a different way to define, I wasn't going to say this, but I'll say it. You can do a different probability distribution on subsets of the coordinates as follows. Pick a random input string, and then look at all the coordinates I such that f is sensitive on that coordinate. And then just call that set of coordinates. Over there I wrote script a sub f. That's a different probability distribution on subsets. And there's some not fully understood mystical connection between that random variable, script a, set valued random variable, and this script s. So for example, one thing we just proved is that these two random variables, if you look at their cardinalities, the mean is the same. We just showed that. It's also a fact, it's not hard to prove, that the second moment of their cardinality is the same. But then that stops working for higher cardinalities. But nevertheless, Rocco and others conjectured that maybe Gil Kalai was sort of initiated this idea that these two random variables have some special ununderstood connection. Rocco and others conjectured that the moments are approximately the same. And if that were true, then they can get some corollaries about the sensitivity conjecture. So there's some yet to be fully understood connection between these two random variables, these set valued random variables. Okay. So let me say a little bit more carefully what I was saying there. So an immediate corollary of this fact, if we use Markov's inequality, it's appropriate being in St. Petersburg, is the following. The probability that the cardinality of the spectral sample is bigger than its expectation over epsilon is at most epsilon. Well, its expectation is average sensitivity. Okay. And this is exactly a Fourier concentration statement. This is saying that the sum of the squares of the Fourier coefficients on sets of cardinality bigger than this is small. And that's exactly the thing that you can plug into the learning algorithm. And this is nice because this doesn't involve the Fourier coefficients inherently, right? It's like some easy, hopefully easy to understand combinatorial property of the function. So we get this by passing through the Fourier coefficients. So as a corollary of this and the low degree algorithm, low degree algorithm, learning algorithm, learns an unknown function f in time n to the order average sensitivity of f over epsilon. Okay, to accuracy epsilon. Mainly going to stop. Just imagine that epsilon is like 1% or something. Okay, so yeah, now we get a learning result just depending on some nice property of the function. It passed through Fourier analysis, but actually there's no Fourier analysis in the final statement. Okay, so now I'd like to show you some, actually, I guess the last few things I'll do is show you a couple of examples of this, the use of this. And I guess the first algorithm example application of this I'll show is the problem of learning monotone functions. So I ended the last lecture by telling you the result that given a random example access to an unknown monotone function, you can learn it in time something like n to the root n. And it's going to come directly from this. So the learning for monotone functions, or learning of monotone functions, comes exactly from this simple fact if f is monotone, then its average sensitivity is at most root n. That's 1 times root n. Okay, and the proof of this is pretty simple. Okay, well, average sensitivity of f is the sum of the influences. Okay. Now we use this fact, I guess I probably erased it, but for monotone functions, there's a different expression, or equal expression for the influence. It's just the degree 1 Fourier coefficient, the cardinality 1 Fourier coefficient associated to that coordinate. Okay, this was by monotonicity. That was that picture with the edges of the hypercube split into 2 types, the plus and minus. Okay, so the next thing I'll do is just write the definition of this, or if not the definition, the basic formula for f hat I. I'll keep the sum here. So it's the expectation over x, it's the correlation of f with xi. Okay, that's a simple formula for f hat I, the correlation of f with xi. Okay, and now I'll do whenever you face this, of course, you just reverse them. That's basic life strategy. So this expectation of the sum actually, the f of x part doesn't depend on I, so I can factor that out. Let me do that then. I'll put f of x here. Sum I goes from 1 to n of xi. And now I'm getting to be sort of home free here. I can do something very simple. You pick x at random. This is some number between minus n and n. This number is either plus or minus 1. So I can just upper bound this whole thing by the absolute value of this part. Let me change that to a less than or equal to. Expectation over x, absolute value of sum of xi. Okay, and now there's no functions or computer science left or anything. It's just I pick n independent plus or minus 1s, I add them up, and I take the absolute value. I guess you may know that that's an expectation proportional to root n. In fact, well, you can use Stirling's formula to get it very exactly, but another thing you can do, we just say it's at most the square root of the square. This is just a trick. You can do this final calculation however you want. This is one way to do it. Okay, let's Cauchy-Schwarz. And now what happens? Imagine you expand this, like open it up. Well, you'll get the sum of the xi squareds. Well, xi squared is 1. So this is just going to be, this whole thing will be n. And then you'll also get the expectation of sum over I not equal j, xi xj. But this we did very early on, right? If you take the expectation of xi xj, it's 0. So this whole thing is 0. Okay, so finally we get this is equal to square root of n.
So why don't you just do Cauchy-Schwarz right there from sigma f hat?
Yeah, you could have done Cauchy-Schwarz here too, actually.
The one before, right?
Oh, where?
Sigma of f hat divided.
Oh, yeah.
Possible.
Oh, yeah, that's much better. Thank you. I think that's, yeah. Thank you. Yep. Good. Should have prepared better. Yeah, Rahul is saying, here's a simpler way. You can say this is at most by Cauchy-Schwarz again, square root n times sum over I f hat cardinal I squared. And then you just have to say, well, this thing is at most the sum of all the Fourier coefficients, which is 1. That's a better way to finish. I guess you can do this if you want to get like, I think it's like actually bounded by square root 2 over pi times root n or something. We don't care. Okay, good. Thank you. Okay, and that's it. So this is how you get like the learning algorithm for monotone functions that runs in time like n to the root n. Okay. So I'll devote the next maybe 15 minutes to one more example. And luckily I have Ben's nice setup. We'll talk about this example. So I'll tell you about this for same story for AC0. We'll say we want to learn AC0. This is constant depth and/or not circuits. Great. So let's recall. I'll use slightly different notation, but okay. So we have this notion of random restrictions. It's the most basic kind that's been described, with a certain star probability. Ben called it P. I call it delta. I can survive calling it P. Sure, I'll call it P. Okay. So let me, instead of using capital R, I'll change the notation here. So what does this mean? Remember, you pick a random subset of the coordinates to be stars. You pick each coordinate to be a star with probability P. So I'm going to call that, I shouldn't use capital S, so I'll use J, and this is Ben's notation, a P random subset of N. This means you include each of 1 through N into capital J with probability P. This is the stars. And then you also pick, let's say, Z uniformly at random from plus or minus 1 to like N minus J. Okay, so these are like the plus or minus 1s, or Ben called them 0 and 1s, that you plug into the non-star coordinates. And these two together, like I guess you would say R is sort of the combination of J and Z. And Ben called it F harpoon R. Sorry, I'm going to call it F's of J and Z. Is the restricted function. Is the restricted function. It maps plus or minus 1 to the J into plus or minus 1. Okay, so sorry for the notation differences, but that's a random restriction. Okay, and one more thing, let me say this. We usually think of F, the restricted function, as just being a function of the J coordinates, the star coordinates. Sometimes, though, I will also think about it as a function that's still of N coordinates that just happens to not depend on the coordinates outside of J. Sort of just notation. Okay, so one beautiful thing about random restrictions, in addition to all the things that Ben told us, is that they also play very nicely with this average sensitivity concept. So here's a proposition that is not hard to prove. Suppose you pick a random restriction, and then you look at the average sensitivity of the restricted function. How does that relate to the average sensitivity of the original function? Well, the best thing that you could hope for is true. It's just equal to P times the average sensitivity of the original function. And I think we can prove it even in this space. Let's see. So remember, the average sensitivity is the sum of the N influences. So here I have the sum of the N influences. And here, I'm going to think of the sum of the N influences on F, the restricted function, in this way I was telling you before, where you imagine F depends formally on all N coordinates, but it actually doesn't depend on the coordinates outside J. So if I fix a particular coordinate, I'm just going to see what happens to the influence for the random restriction. Well, what can we say about the expectation over this random restriction of just the influence of the ith coordinate on the restricted function? Just put a question mark there. Well, unless this star set J contains I, this influence will be 0. Because if you, this ith coordinate doesn't become a star coordinate, it's going to have no influence. It doesn't affect the function. But if it does, right, the probability of this is exactly P. So with probably 1 minus P, it's going to be 0. Probably P, it's going to be a star coordinate. And now, let me just say this half in words. If you condition on J containing I, let me just say, I'll explain it in words. The experiment is the same as on both sides. So like, what I mean by this is, like, let's look at what's going on here. The expected average sensitivity of the resulting function. But let's condition on I being a variable that's in J, that sort of stays alive. So first you pick the random restriction that gives you some stars, which include I, and then some other random, uniformly random bits for the rest of the coordinates. But then what do? We compute the average sensitivity of the restricted function, which basically means you fill in all the remaining coordinates, star coordinates, except for I, at random, uniformly. And then finally, I is the only star left, and then you imagine change the two possible values for the ith bit and see if that affects the value of the function. So that's what's going on here. But it's just, you've ultimately done the same thing as over here. You've like picked a lot of uniformly random bits for all the positions except for I, and then you've imagined the two different ways to fill in the ith bit and see if that affects the value of the function. Sort of the conditional expectation of this condition on J containing I is exactly the average sensitivity of F. Okay. Probably could set it up with the timestamps the way Ben did it. Just give I like the lowest timestamp and all the other ones higher timestamps. But anyway, that's the end of the proof. I said the rest of the proof in words, but are there any questions about it? Okay, great. So let's take that as a given. So that's very good, because now if you could figure out something about this, which actually looks a bit harder, but if you could figure something about this, you'd conclude something about the average sensitivity of F. And then if you concluded that the average sensitivity was small, you could conclude that you could learn the function quickly with this low degree algorithm. So how can we get a grip on the expected average sensitivity of the restricted function? Well, you may start to guess. The whole point of these random restrictions, together with AC0, is that you get some nice facts from the switching lemma. Okay, so what does the switching lemma tell us? If you look for like a few seconds and try to get the parameters right, which I might not quite have done, but if you do get the parameters right, you can conclude the following. If F is computable by a size S, and maybe S should be at least n here, depth D circuit. Sorry, I'm going to use D instead of D plus 1 like Ben, although I like the D plus 1. Maybe I should try it. Well, then, roughly speaking, for P not too small, I'll write the parameters essentially in a second, but for P that's not too small, the switching lemma tells you that F, the restricted function, has a decision tree that's quite shallow. Of height, at most some small k. I'll get the right parameters in a second with very high probability. Okay, that's the high-level picture of the switching lemma once you plug in p and k appropriately. But what can we say about the case when it has a decision tree of height at most k? What does that imply about the average sensitivity? Anybody want to say? It's also at most k. There's two ways to see that. One is we have this average sensitivity formula that says it's sum over all s, cardinality of s, f hat s squared. We also have that if you have a decision tree of height k, when you write it as a multilinear polynomial, its degree is at most k. Which means that in this sum, like once cardinality of s is bigger than k, all of these things coefficients are 0. So this is at most k. Another way to see it, you can see it combinatorially. If you have a decision tree of height k, you pick a random string input that takes you to some leaf And you ask yourself, how many different coordinates could I flip that would flip the outcome of the function? Well, the only coordinates you can flip that could possibly flip the outcome of the function are the variables in the path that took you to that leaf, of which there are at most k.
Worst case sensitivity.
Yeah, so in fact it has worst case sensitivity at most k, not even average sensitivity at most k. Good. So in particular that means like almost surely you get like a super low depth, like a super duper low depth decision tree, which means almost surely the average sensitivity of the restricted function is super small. It should mean that the expectation of the average sensitivity is also small. That's indeed the case. I think particularly, so this is where you have to like squint at the parameters. Hopefully I got them right. Think of delta as like a 1/6, 1 over 20 log s to the d minus 1. Roughly 1 over log s to the d minus 1 is like the right p in order to crush a depth d size s circuit. This implies, if you look at the switching lemma for a couple of seconds, that if you do the random restriction, the decision tree depth, the expected decision tree depth of the restricted function is at most 2. You know, Sven was telling you, actually, I mean, when you do these random restrictions, it almost always collapses it to a constant function. But
Is it 1 over 20?
pardon me?
Is it 1 over 20?
Yeah, it's like 1 over 20 times log s. I think I got this calculation right. I mean, it's like a very high probability that you get a very shallow decision tree. Great. So then, good. So now we just have, oh, sorry, this is not delta, this is p. Okay, so now we just have to compare this and this. So we conclude that just the average sensitivity of f itself is at most 2 times the reciprocal of this. I don't know. 12 times, okay, order log s to the d minus 1. Okay, that's 12 times the 20 to log s to the d minus 1. Okay, and this was first proven by Bopana. 2p's 1n. And then actually, Ben actually improved this a little. Ben showed that if it's a formula, you can divide by d here as well, on the inside. Okay, that's great. That's all we need to get a learning consequence. So as a learning consequence, you get that, let me stick with this hypothesis. Under this hypothesis, or not hypothesis, I mean if you assume that you're learning a function computable by a size s depth d circuit, I'll just write it again. Size s depth d circuit, learnable to accuracy epsilon in time n to the order log s to the d minus 1 over epsilon. Okay, so for example, if s is poly n, and epsilon is constant, and d is constant, and this is quasi-polynomial time. Okay, which is pretty good. Now, I should add, any questions about that? I should add that you can do a slightly better analysis of the Fourier spectrum of AC0 functions. In particular, one that has a better dependence on epsilon. Okay. So if epsilon is constant, like then this is the best. But if you think of epsilon as very small, like maybe epsilon itself is 1 over poly, this is not so great, and you can get better results. So let me say the best thing that's known, this was done by Lineal, Mansour, and Nissan in '93. Then Hostad made it better in '01. Then Hostad made it even better in '14. And then Avishai et al. Made it even better in 2015. I think actually we'll hear a little bit about both these things. But they showed slightly better statements about the Fourier spectrum. So like probability over the spectral sample of S, F. But this thing is bigger than K is at most epsilon for k. Instead of log s to the d minus 1 over epsilon, you get order log s to the d minus 1 times log 1 over epsilon. Okay, that's a lot better because then you can take epsilon to be 1 over poly n and still get quasi-polynomial time. Okay, kind of mostly done, but I'll just tell you one additional thing. So this average sensitivity is nice. It's like a combinatorial property of Boolean functions that allows you to get learning results and by looking at Fourier concentration, by proving things about Fourier concentration. There's another more strong way to get bounds on Fourier concentration using a different concept. And I'll just tell that concept to you, but won't prove anything about it. And it's kind of connected. You might say, oh great, AC0, we did it, like and or not circuits. You might say, hey, next step would be TC0. This is constant depth circuits with threshold gates. So remember that a Boolean threshold function, or threshold gate, is a Boolean function. Here's another case where the plus or minus 1 notation is nice. F of x is of the form sine a0 plus a1 x1 plus dot 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 plus an xn, okay, for some fixed ai's in the reals. Okay, so the most famous example of a threshold function is the majority function. That's when you take a0 to be 0 and all the rest of the ai's to be 1. This gives you majority. Okay, so another way to compute the majority of a bunch of bits is add them all up and then take the sign. Great. So we might be interested in the learning the class, I don't know, TC0, which I guess nothing is known about that, but you could start small and just try to ask about learning even less complicated classes than TC0, like learning a single threshold function or learning like functions of the form like one gate on top with like threshold functions on the bottom. Stuff like that is more tractable for learning. And you could try to do this by the same methods. So you might ask, okay, what about the average sensitivity of functions, threshold functions? Maybe that's small, and then we can learn them just like a single threshold function efficiently. Well, unfortunately, it's not that great. So we saw before that the average sensitivity of the majority function is theta of root n. Okay, so since majority is a threshold function, it tells you if you want to use, let's say, the low degree algorithm, well, if you just want to use this average sensitivity method to learn the class of threshold functions, it might take you like n to the root n time, which is not very good. This implies that in fact, it's not hard to show that actually average sensitivity, this is a bound on the average sensitivity of f for all threshold functions f. It's actually basically because threshold functions are monotone, basically, or unate, basically. So this root n bounds applies to them too. Anyway, this tells us this: the sum of all sets bigger than root n over epsilon f hat s squared is at most epsilon for threshold functions. But this bound is very, very far from tight. So actually, threshold functions have much, much better Fourier concentration. It's also true that if f is a threshold function, the sum over sets S of cardinality just bigger than 1 over epsilon squared is order 1 over epsilon, is order epsilon. Okay, so well, I guess it's slightly worse with epsilon, but basically if epsilon is a constant, this tells you that almost all the Fourier mass of threshold functions is only on constant degree monomials, not on like up to root n degree monomials. Okay, and this allows you to learn threshold functions in polynomial time and stuff like that. But it uses a generalization of this average sensitivity called noise sensitivity. Okay, so if you're interested in this stuff, noise sensitivity is a really nice topic that also connects combinatorial properties of Boolean functions to their Fourier spectrum and mixes really well with threshold functions. So you can get lots of other learning results this way. Okay, I'll stop here.
Are there any questions for Ryan?
No?
I mean, in this result, you basically upper bound average sensitivity in the worst case, right?
Yeah. Like the, yeah.
And then you get this learning algorithm that is slightly worse. So what's the difference with that?
Okay, so they proved this not by passing through average sensitivity. But they basically proved this, or versions of this, by just saying if you do a random restriction to an AC0 circuit, it's very likely to be a decision tree, which tells you more than just like sort of the average cardinality of the spectral sample is small. It really tells you it's like totally capped by this decision tree height. And then if you sort of run, you can understand how does like the Fourier, if you know that the Fourier spectrum is like capped at a certain height in expectation or a random restriction, what does that tell you about the Fourier spectrum of the original function? And if you work not very hard, you get almost this result. And then if you work a little bit harder, and we'll see it next time, in a few days, you can get this strong result. So it's a similar argument, but more involved. Yeah?
What happens if you're trying to learn, say, functions that take values in their range outside 0, 1?
Yeah.
Like rational or integer or even finite field or something like that?
Yeah, I was asked this question by Newton, I think, as well. It's basically actually all the same in some sense. You can still do the low degree algorithm if you hope that the function has almost all its Fourier coefficients on large Fourier coefficients on small sets. The low degree algorithm will still work even for, let's say, real valued functions. You'll get error in the squared norm loss, like the expected value of the square of your hypothesis minus your function will be small. The one thing you're lacking is then you have to say, okay, for like my real valued function, how do I show that it has most of its Fourier coefficients on small sets? You can try to do that somehow. The thing is, this average sensitivity and noise sensitivity don't apply so well to that real valued functions, because they're looking at like what's the probability f's value changes when you flip a bit. It's not so natural when the values are real. So you can say some things, but you might need to look for other methods to show that Fourier concentration is good. Any other questions?
Okay, let's thank Ryan again.